Okay, Fuad, are you okay if I go ahead and start things off?
Yeah, please.
Cool. All right. Well, hello and thank you everyone for joining us for this month's SNOMED CT research webinar. I am Susie Roy. I'm the Customer Relations Manager for the Americas and the host for this research webinars. I just wanted to give a couple of really quick, just overall housekeeping items for those who have attended the previous research webinars. You're used to these, and for all of us who have been attending a lot of Zoom webinars, these will be old hat. But as you're coming in, you'll notice that everyone is currently muted and videos are disabled except for Fuad and myself. But as we go along with today's presentation, go ahead and post your questions into the Q&A box. And at the end, we'll have a moderated Q&A session. Other than that, our presentation today is being recorded, and we'll make the recording available as well as the slide deck available later this week or probably early next week. So as I alluded to, this is the research webinar, but for those who are unaware, we also have other SNOMED CT webinars within our web series. We have a clinical webinar and an implementation webinar where they focus more on the clinical and on the implementation of SNOMED CT. Our research webinars are of course, focused on research on and with SNOMED CT and with terminologies and informatics. To view any of these web series, you just go to snomed.org/web-series, and it'll take you to the list of our previous webinars as well as any upcoming webinars in any of those 3 tracks. We also have a SNOMED International YouTube channel. You can like and subscribe to our YouTube channel, and you'll be notified anytime we post any of our SNOMED International videos. But you can also find our SNOMED CT research web series, which is kind of down here on the bottom of the page, as well as the clinical and implementation tracks. I highly recommend all of you to become SNOMED International YouTube channel subscribers. If you wanted to be notified of any upcoming SNOMED CT research related news, you can join our research reference group. This is a Google group that I kind of manage. Essentially, I just push out a couple of notices per month, usually about 2 to 3 notices, letting you know of when the SNOMED Expo is coming up, as well as upcoming research webinars or when the webinars are posted onto YouTube. So to join, you just need to email me, sro@snomed.org to join. And I wanted to alert you, you might already know, but just in case if you don't, we are currently hosting our call for abstracts for our September SNOMED CT Expo meeting. The Expo is usually in October, so I'm having a hard time saying September, but this year it is September 29th and 30th. And we are looking at doing a hybrid event, but we are very excited that we're going to be located in Lisbon, Portugal. So you can submit your abstract right now if you go to snomedexpo.org anytime between now and April 17th. If you have any questions whatsoever about the SNOMED CT Expo or submitting an abstract, feel free to email me. And last but not least, we are going to, I can introduce our presenter for today. Dr. Fuad Rahman is a Silicon Valley technologist with a deep experience in building cutting-edge big data analytics solutions in the healthcare and financial sectors. He has extensive background in big data modeling and analytics, natural language processing, computational linguistics, and pattern recognition. His early R&D life was spent working on SBIR and ATP/NIST projects, during which time he worked with all 3 branches of the armed forces, US Air Force, US Navy, and US Army. He is the founder of the Apurba, sorry if I killed that word, technologies building on AI-driven 100% computable health information platform powered by machine learning and NLP. He's also an adjunct professor at the Department of Biomedical Engineering at the University of Arizona. With that, Dr. Rahman, I am going to send the screen over to you.
Thank you, Susie. I'm going to go and try to share my screen.
Yep. Perfect.
Okay. All right. So about after the very detailed introductions that that Susie did, I don't think I have to introduce myself anymore. So thank you so much for inviting me. It's a big honor to be here. I've looked at the previous presenters, and it's a huge honor to be here to speak to this audience. So what I was going to talk about today is a lot to do with healthcare data and SNOMED city and machine learning and artificial intelligence. But I thought that before we do anything, we should take a look at the title that I chose for this. It's a good place to start. The title is Computable Healthcare Data, and the subtitle is Challenges and Opportunities of Generating Targeted Insights and Impacting Real Outcomes Using Machine Learning and Artificial Intelligence. Now, let's look at some of these keywords, because I think those are very important before we take a deep dive. Computable, and I'm kind of assuming here that a large portion of the audience here today is not from core computer science background, because we are looking at healthcare data here and healthcare applications here. Computable is a very tightly defined concept in computational science, and it basically, I'm not going to go into the details, but it's what is known as charter-sweep hypothesis, and it's to do with something that can be converted into something that can be computed, obviously, right? But the idea is that this is not really provable, like a lot of things that in mathematics are not provable. And the idea is that you see the 6 different theorems that are on the right side, or ideas. If those can be proven, then apparently, it's something is computable. Now, what that really means is that computation means something is computable if it can be computed by a computer program, not by a machine, not by a human being, right? With a reasonable programming language, which means that it can be broken down into numbers, right? Because computers understand numbers. Now, if we then go to the next part of it, which is, we're going to talk about artificial intelligence and what that really means. What does it really mean? It's a very interesting concept about, how a machine can mimic how humans work, or human intelligence. And the idea is that, the machines become intelligent, they behave like us. In other words, Alan Turing basically said that system that behave like humans. The problem with that definition is that we humans are fairly irrational sometimes, right? Given the same input scenario or variables, we behave differently based on our mood or something else, right? Or who we are with, we behave differently based on our audience, for example. So should a machine or artificial intelligence behave like that? Should it be rational? Should it not be deterministic, meaning that it should produce the same results given the same inputs? So, there are different opinions of it, and we don't really need to go into this today. But what is important for today's talk is what specifically machine learning means. So machine learning is basically making a machine intelligent, which means that it has to have the ability to learn. And it's basically the way the algorithms and how that data is, or experiences are used to actually make a machine learn. That's actually what machine learning is. So it's basically a sub part of AI, or artificial intelligence. So now that we have got that out of the way, let's talk about some healthcare stuff, which is more important to this audience. I talked about targeted insights and what does it really mean in terms of within a healthcare. The insights is something that is derived, right? It's not raw data, and it means that something that we understand and we can actually do something with it. Healthcare data is one of the most complicated domains, for understanding, and making it context sensitive is very important. So I'll give you an example, a simple example. Let's say that a patient walks into an ER, and the doctors really don't know about all the details about this person, so for example, if he came with a signs for a stroke, the fact that he may have broken his arm when he was 3 years old may not be very relevant. That's not really contextually important. What is important is, does he have hypertension, for example, or does he have heart disease? Does he have some other things? So that's what it really means, right? So in our case, we also talked about outcomes, and what does really outcome mean within the context of a healthcare system. Now, outcomes are either direct or indirect, intrinsic or extrinsic, but at the end of the day, it has to have an impact to the bottom line of a patient, right? And it has to have an impact in terms of health outcome, financial outcome, quality of life outcomes, that kind of stuff. So we're talking about how do we actually build software solutions that can actually have real change, make changes in the outcome of a patient. So now that we kind of talked about the title, let's talk about why I'm spending this amount of time talking about AI and machine learning. And everybody you're here, you're thinking that why is Fuad talking about all this stuff? What does it have to do with SNOMED City? Well, the answer is that it has got everything to do with it, and that's going to be the focus of the webinar today. So let's do some thought exercise. Let's do some what ifs. What if machines could read healthcare data? Now, the question you probably are thinking about is, well, I thought machines could read healthcare data. Well, yes and no. Reading data means not just reading it, right? But can we read textual data? Can we read imaging data? Can we read signals such as like a CT scan, which is can be converted into a signal, right? Also, data can be formatted differently. It can be structured, unstructured. As we know, doctors' notes are unstructured, whereas daily charts are structured. Can they do it in different ways? Because it can be stored in different formats. I mean, written, spoken, video, audio, all that stuff, right? Let's go a little bit more like, what if a machine could process the data? Now, what does process mean? Like, process would mean that I look at an image of a car and I'll know it's a car, right? So that would be even great, right? Even better if we can do that, right? So we can process the data, we can understand, we can at least start building a form of some sort of understanding. But then ultimately we have to understand the data. What does it really mean? And that's where semantics come into play, right? So raw data needs to be converted into something that we can read, process, and then eventually understand. In my mind, the way in order for a software system to do this kind of stuff, there are some prerequisites. One is that we need to have some sort of unique identifier names for all the different concepts. Like fever is a concept, right? And then we need to somehow be able to have a references to the relationships, like maybe why can a fever come, right? I mean, gunshot wounds can start, some sort of that, or it can be viral. So there are relationships and other things, and we need to have some sort of understanding of this. And then the question is, if we had that, what do we do with that then? then the important thing, what from a computational perspective, is that, okay, so if we can get that level, we can, let's start, if the machine can identify a clinical concept, and then maybe the machine can tag it, meaning that it can identify and uniquely define what these kind of things are. And then once we have that data, then maybe we can model these relationships in some way. And once we have a model, maybe we can learn from it. And what do we learn? We learn some sort of patterns, for example. So that's actually the computational way of looking at it. And what it really mean is that we have to find a way to convert data into some sort of common format. And we need to have a way to make them interoperable so that different algorithms can work on it. And which, again, in layman's term, means that it needs to be all get converted into kind of data, which basically what I call democratizing the data. And if we can democratize the data, then the data is now computable, as we say. And there it is. We have come full circle. The good news is that we do actually have the foundation of a lot of these things, which is SNOMED City. That's exactly what it does. And let's start there, and let's see where we can go from there. So I'm assuming that I do not need to spend a lot of time in this section, because I'm assuming most of you, if not all of you, know about SNOMED City. As we all know, that it's a collection of codes, terms, synonyms, definitions, and there are thousands of concepts in it, right? And the concepts are very well defined. There is a description area, there is concept code area, relationships area, there are semantic tags, reference sets. It's very well structured. So stuff that I was talking about in the beginning, now it's starting to make sense, because okay, we have some sort of identified a taxonomy, at least, that identifies all these concepts and some sort of relationships. So let's see how we can actually then use that power and then do something with a machine. Now, I'm being a machine and I'm trying to do something with this. Since every concept has some sort of synonyms and everything else, we need to be able to find their fully specified name, what other preferred terms are there, and what the references are, or the mappings are, right? And the step 2 is that we have to define those relationships. And as I'm sure this screen is, this type of screens are very known to the audience here. All the relationships are laid out in parent, children, that kind of, and then there are descriptions, qualifiers, related concepts. And then there are obviously hierarchical things. So a lung disease is a infectious type of pneumonia, which is actually a viral pneumonia. So relationships. And then once we know that, then we should be able to do different type of relationship, is a finding thing, different type of associated morphologies and stuff like that. So then eventually we have some sort of meaning, which is a semantic tag, a clinical finding, organism, procedures, that kind of stuff. Finally, we need to now make this computable. So if there is a text that says 3rd-degree burn of left index finger caused by hot water, can we do this? So what I basically did here is I took the corresponding concept and just added the concept here, right? And as you can see, hot water is a concept, and it's a kind of an agent. And then there's a finding site, there's a location, there is a morphology, and there's a disease. So suddenly what we can see is that a sentence or a sub-sentence, part of a sentence, can be expressed in terms of numbers and their relationships. And that's the description logic that we're looking for. And that's something that machines can start to process. So the question is, okay, now that we can do that, why do we even need machines for this? Well, the problem is, what we have done so far is we need a subject matter expert who understands the taxonomy and understand how to tag all this stuff. It's not scalable. I mean, it will take hours and hours, days sometimes. So we cannot really democratize the data the way we want to. But what if we could automate all these things? And that's where I think would be very interesting to take a look at that. If a machine could do that, then then that would be great. So the two questions that I'm basically asking myself is, even if a machine can do this, and the second is that can the machine can do this at scale, meaning that it can do it accurately, and but it can do it faster with exponentially larger data sets? And the answer is yes. So let's take a look at how we can do that. So now we are really looking into the computational aspect of machines, and how we can actually build a system like that. So the starting point of that is actually to take all these relationships and convert it into machine readable format. And this is not something that we have uniquely done. Others have done before us. I'm just showing it because it's always the first step. So what we did was we converted we took the SNOMED city and we converted that into a JSON format. Now, those of you who have a computational background or CS background would know that JSON is a type of data structure using Java, which basically is designed for read by a computer. So we found a way of taking all the relationships, all the concepts, and we converted into a JSON format. And I'm not going to go through the details here. There are like 4 or 5 slides here about how we took all this stuff, and this would be actually the slides are going to be, I believe, distributed, so you guys can take a look at that. But there are actually outside resources available that shows how this can be done. But the end result is that once we convert it into a kind of like a computer readable format, we basically now have a database that does exactly what we want it to do, which is can be put into a format that a machine can crunch very fast. And this is what it looks like once it's done. So all the relationships are there and all the numbers are there, and it's all in the format that the machine can parse very fast. Now, by the way, I've talked about JSON before, but there are tons and tons of tools free tools out there that you can use. You don't have to use a proprietary thing for this. So now that we have,
sorry, Fuad, Susie, before you go on, had someone ask a question just for clarification, and
sure.
Wanted to make sure that this was correct before, because that'll kind of solidify in understanding some things. So we had someone ask JSON LD, and I just wanted to confirm that that's JSON for linking data.
Yes.
Okay.
Yeah.
Thank you.
Absolutely. All right. So let's go back to the modeling part now. So now once we have the data, the SNOMED converted into some sort of a computer readable one, what can we do with this? So before we go into details of it, let's talk about some concepts, more conceptually. So let's say that we have an EHR which has doctor's notes, and wouldn't it be nice if the machine can read the doctor's notes, automatically identify all the nice clinical concepts, and then tag it to the corresponding SNOMED concepts? And that's what we want to do using our machine. And all the approaches that I'm going to talk about quite a few approaches here. They're all going to try to do that. They're going to try to read it in natural language. And those of you who do not have background in NLP or natural language processing, it basically means like, when we speak, a language, English or whatever, it's in a linguistic format, right? And the machines don't do that well in understanding it. NLP actually converts that, understands that. Now, so that's the barrier number one. But then we have to somehow match it against SNOMED, right? And find out what concept is related to it. Now, think about this. A doctor's notes may have pages and pages of content. So we have to understand what a paragraph is, what a sentence is. We have to understand what a verb is, what a subject is, what an object is, what are the relationships between all these things are. So it's a non-trivial, let's say, problem. So one of the first things that we're going to talk about is what it's commonly known as TF-IDF process, which is TF is basically a term frequencies. Basically looks at number of occurrences of a specific term in a document. And DF is document frequency. If you have a lot of sample documents, it looks at the frequency of that. And IDF is basically the inverse logarithm of that, or domain frequency. So let's not worry about the numbers too much. The idea here is that we're trying to find out how commonly shared in a specific domain these words are, because as you know, every SNOMED concept also has words in it, and we're trying to match those words. That's what we're trying to do. And cost similarity is one of the most common methods that people use, and we use that too. And the result is fairly interesting. The result is that if we have text like that, I don't think you can read that too well, but if you can see that we actually have brought out specific disorders, myocardial infarction, disorder of the back, disorder characterized by pain, all that stuff. The machine is identifying those concepts automatically by looking at the text. No humans involved in this process at all. So what we basically are trying to do is, given a medical record written in natural language, can we find a diagnosis? That's what we're trying to do here. And it looks like we can identify quite a bit of them. This one is a little bit more readable, I think. And if you can see that, if we look at it sentence by sentence, he has a past medical history significant for a myocardial infarction in 1994. We can actually identify a lot of that from that, right? And all of this happening by the machine, right? And this is, and you probably heard about supervised machines versus unsupervised machines. Again, I'm not going to go into an AI lecture here, but basically, there are ways of training a system, and there are ways where you don't have to train it; it just knows by ingesting content. And these are one of those things where you don't have to really train it. So we can also do it on a sentence level, by the way. Instead of looking at the entire subsection or a paragraph, we can just take a look at a sentence and we can get that sentence. It is basically the same example I showed before, just in more detail. So some of the advantages is that, as I said before, there's no training required and implementation is fairly easy. But there's some disadvantages too. I mean, it takes longer. You have to really process the documents beforehand. If I throw in a new document, you have to add it, and there are some thresholding or estimation required, which requires a lot of guessing, right? So, but it's a good starting point. It's a good starting point in the sense that we can at least start getting some interesting automation by processing the text. Now let's talk about another approach where it's word to vec, and which is basically what we do is we basically take each of the words and we put it into some sort of a domain. And again, I don't want to lose the audience here, and I don't want to go into details here, but it's basically you take every word and turn it into a vector, right? In terms of computational space, and similar words will be basically coexist in the similar space, like king and queen, because maybe they're mentioned more in common, but man and book probably are not. So that's just an example. So what we did, we used the word to vec to convert all the full scientific names, specifically. We didn't do everything. We just took the full scientific names and we converted them into numerical format, right? So that a model can do that. And for us, every word, we turn it into a vector of length of 125, and all concept names were actually went to a length of 45 because they have varying length. So let's take a look at an example. And what are we trying to do? What we're trying to do is we're asking ourselves, can we build a model that can predict the probability that a sentence is correct according to SNOMED city standards? Or in another way, we can say restate that same problem. If somebody writes a sentence, can we reorder the words to make it more processable by machines? So what we did was we basically took these embeddings to train these sentence validation models, right? And then we ran some tests, and the results are very interesting. So we start with an unordered list of words like these. So off, neoplasm, malignant, all that stuff. And the machine can generate this sentence. So the question would be, why would this be of interest? Well, this would be of interest in many ways. For example, maybe it can be used as a tool to flag sentences that are confusing or doesn't make sense. It can be used as a kind of like a tool to kind of prompt when notes are being written, or it's kind of can be used as a pre-processing for future learning, for a modeling and prediction, and we're going to talk about that a little later. So there's a lot of applications of that. So let's take a look at now other approaches. So far the stuff that we looked at is kind of you don't have to train that much, but let's take a look at more deep learning methods, stuff where you actually have to model and train and all that stuff. So let's see that if we can get a model that can take a sentence to a specific vector representation, and we use BERT. BERT is a bidirectional encoder representation from transformers. It's something that researchers at Google first did. As you know, they have billions and billions of sentences, so they were able to do a lot of very interesting stuff. And it's what they call a language model. Basically, it can when you type your text these days, it will predict the next text, right? Next word, right? That's what it's trying to do. It's using a language model to guess what the next word should be based on billions of samples it has seen before, right? So we used BERT first, and the problem is still the same. The problem was, can we identify SNOMED city concepts from a free format doctor's notes, right? We use BERT and it doesn't work that well, unfortunately. So we kind of, and we think we know why, because BERT is more generic. It is generic, not more. It is generic. It looks at the language from a language perspective, and it's probably simply too generic for the clinical language that doctors use and patients or nurses use. By the way, this is a good time to tell you that every domain has their own language. Like before I went into clinical area or healthcare area, I was heavily into financial document processing, and those languages are different. The words are different, concepts are different. Just like you have SNOMED on the healthcare side, we have US GAAP on the financial side, right? GAAP, GAAP, generally acceptable accounting practices. That exactly does the same thing as SNOMED does, which is identifies all financial concepts and then creates relationships between them. And I actually did some work about 10 years ago where we did pretty much the same thing. We modeled these relationships, and we were able to, for example, extract any number, and you can tell, we could tell, the software could tell what that number represents. For example, is it a loss, annual loss or quarterly loss, and things like that. Anyway, just a side conversation there. But anyway, coming back to the clinical work, clinical language that is commonly used. So we actually use other type of models to see if we can get better results. One of them is Roberta. The other one is Universal Sentence Encoder. The other one is Sentence BERT. BERT specifically designed for sentences. And let's take a look at some of these results. So because they're optimized for specific ones, I'm not going to go into how they're optimized. You can take a look at, just Google them and you'll find lots of references for this. And you'll see that, and the second one is Universal Sentence Encoder use, and that's again from Google. And again, I'm not going to go into the details of this. The third one is sentence BERT or SBERT. But let's look at some results. That's what I think it's going to be more interesting. So it's the same same sentence again, same example again, and you see that we can now start getting the codes, SNOMED codes out of this. For example, calcium channel blocker contraindicated. So very, very specific one that is coming out of the sentences, right? We can also take a look at the results coming out of the universal sentence encoder. And the results are like this. Let me just cross this, and you can see the different results. And we used the sentence level BERT, and we got results. And then we will start thinking about, okay, what about we give them phrases instead of the machine phrases instead of the entire sentence? Because as we know, the quality of the write-up in the medical in the notes are not always the greatest. And even with phrases, we can actually get fairly good results, as you can see here. So let's now look at, now that we know that the machines can be trained to do like some of the SMEs work, then the question is, okay, now we can do this at scale. We can process millions of these documents. What do we do with those documents? So one of the things we can do is maybe we can start building an application where we actually start building something which looks at how strong or how confident these machines are. And one very common way is actually by voting them. And just to give an example, we can have two of these systems voting for one particular SNOMED city code, or we can have three of them. The 1, 2, 3s are different type of like 2 votes. The third one is a 3 vote. And what we have done is we basically take a look at the top 5 suggestions and try to find out what the commonality is between them. And we've found some very interesting things. If we look at that, now suddenly a lot of the noise, as we say, is now not there anymore. So now we get very distinctive, shortness of breath. It becomes shortness of breath because all 3 models or all 2 models found it. Similarly for the sentence BERT and use, we found shortness of breath. For Roberta and use, we found similar things. And if we use all 3 of them, we found similar things. Why am I showing all this stuff? Because you can see in all of these examples, we can actually start building a software application now, which is a little better than just research, right? So we're talking about transferring the research or transforming the research into the applications area. So I'm not going to go into a lot of these results because there's a lot of results, but you can see some metrics, and we see that a lot of them are actually common, which is really good indication that these results are fairly concrete. So what have we shown so far? What we've shown so far is that for every sentence or phrase, we can take fully specified names and get and identify other things out of it, right? And get even a confidence score. So now that we have all these things, what can we do by putting them all together? So one idea might be, we can do summarization of patients' doctor's notes. So some sentences may be relevant, others may not be relevant. And in order to do summarization, you have to understand every sentence, you have to understand the whole concept, and then put them all together. So it's a much harder job. Pretty much everything that I've shown you so far, you have to use here in order to get a good summarization. And we have actually done that, and we know that we can actually do summarization as well. I'm kind of running out of time, so I'm going to go a little faster here. We have actually done summarization, and we've shown them to doctors, and looks like we can do very nice summarization out of this. And this kind of an example of the system that we build. And these can be very fast, very accurate, especially statistically speaking, extremely accurate. So that's just an example of what we can do, right? So an example might be, we take these summarized sentences and rerun this again and get even better at this, right? So again, I'm not going to go into details, but just imagine that a machine can, in the background, kind of like an offline mode, monitoring all the nodes. And what if, now let's talk about all what ifs. What if we can take, a machine like that works, and then think of a hospitalization scenario. A patient is hospitalized, notes are getting added over, every few hours, and the machine is reading those things, and as it reads and it generates all these CP codes, it can start generating some hypothesis about where this is going. And it's just an example I'm talking about, and I'm doing a thought exercise. And maybe what we can do in the future is that we can now look, if we had thousands and thousands of patients before in our system, maybe the system can find out and say, you know what, these things are looking really close to patient number X, Y, and Z. And let's take a look at those patients. I mean, what really happened to them? What happened in day 4 and 5 and 6? If this treatment actually continues, we can do a lot of this very interesting stuff in the future. And again, none of these actually, I'm suggesting that we'll replace a doctor. It's not that. It's to do, what it can do, however, is to really assist a doctor by looking at these very detailed signals captured in textual and non-textual formats, which a doctor doesn't really have time for, right? So let's now skip through. As you see, we have too many results here. I'm gonna just skip through it, and let's go to the final step, which is basically, let's conclude about what we can do about all this stuff. Yeah, what I try to show today in this webinar is that machines are doing fairly well these days. We can actually read language as they're spoken, right? We can understand them. We kind of know what it means. And then we can even have machines now that can model the SNOMED's, architecture, relationships, concepts, and actually start identifying these codes directly onto the text and no use of humans. And that's a big thing to say, because once we have that, then we can do a lot of things. For example, I gave you one example where a machine might be monitoring the doctor's notes over a few days of a hospitalization. But we can do other things. For example, if we have enough data, we can actually predict the onset of diseases, for example, given a set of healthcare records, what patients would be more vulnerable to, say, COVID-19, right? We know that not everybody gets sick or infected. Even if they get infected, would it be severe, or would be a simple case, or would it be asymptomatic or symptomatic? All that stuff we can actually maybe predict. And we can also do this on everything I've talked about so far is kind of individual level, but we can move to a group level or population level. And once we have population level data, we can do a lot of things. Like, for example, we can look at maybe inherited diseases, right? I mean, given a population of patients which have been identified or diagnosed with a specific type of inherited diseases, maybe we can combine genetic data and start actually finding out real relationships between their DNAs and their environmental factors and where they are in a particular step of their life. So I would think that's a good place to stop. We have 15 minutes left. I would get this back to Susie, and thank you so much, everybody, for your time today.
Thank you, Fuad. That was absolutely awesome. Everyone on this webinar just received a master class from Dr. Rahman on the representation of SNOMED CT and text mining. That was so cool. Thank you. But I mean, this is really important. Not only is it, just cool to see, but also being able to extract and identify the SNOMED CT concepts directly from a textual format. I mean, here in the United States, that's where I'm currently residing, clinician burden is a major topic, and having, I mean, we all know with SNOMED CT, it's not meant for, memorizing all of the codes like you would in a classification or anything like that. The real, we do have some things where it's structured and it's drop downs, but again, it's a drop down field. A lot of that data is actually in the text formats of your records, and also, let alone, as you also saw, we have all of this deep information also in publications and everything. So the ability for utilizing some of this work just goes beyond the EHR and really how we can use this for helping health. So that was excellent. Thank you so much, Fuad. So we do have a couple of questions in the Q&A. So I'm going to pull that up now.
You want me to stop sharing my screen?
Oh, yeah, if you wanted to. There you go. Hi. All right. So first question, how would you develop an early warning risk score for emerging health issues, for example, behavioral health?
So that's a really good question. So for especially for behavioral health, we know that it's highly structured, and we can actually get population level data. And what we can start doing is we can start building models that can create the association between the patients and their records. And once we can start doing that, we can then augment that with other information. So it is definitely something, where we think that it's going to be very interesting.
Another question, can this type of service be easily integrated into existing platforms, for example, analytics or population health?
Yeah, so that's another good question, because as you know that everything that I've shown is kind of like a layer on top of data. So we can pull the data out of any existing systems, right? It's agnostic to the platform or the EHR. So it's EHR agnostic or platform agnostic, which basically means that I can pull the data out of any existing system and run this as a separate layer. It may not even have to, your data may not even have to leave your premises. And that's, as we all know, that healthcare data is very sensitive, privacy and otherwise. So these kind of systems can basically, I mean, as there is a type of systems these days where instead of pulling the data out, you actually push the data, this algorithm in. So you can run it locally and actually derive, secondary information, pull it out of in a server and do other calculations. So yes, the answer is we can run it independent and as a separate layer, and it can run on top of an existing system.
Great question, and that's actually really good to know, because yeah, I was kind of thinking, how would you actually lay this, within a system, but actually being able to independently, yeah, gives it a lot more ability to use it in different sorts of information and analytical, situations. Another question, what is the optimal phrase string length needed to accurately identify a concept for the medical domain? Assuming that the optimal phrase string length for identity, the concept may change based on the domain, such as banking versus healthcare.
Right. So this is actually obviously coming from somebody who has trained on systems, and the
John is my guru for many things.
Right. So the answer is not going to be as impressive as the question, unfortunately, because a lot of it is trial and error. And a lot of it is trial and error in the sense that we, most of the cases, we do not have ground truth data for these things, because it's not like, let's think about a very simpler problem where OCR, for example, optical character recognition. A is an A, B is an B, C is an C, and a human has labeled that. So that's my ground truth. In healthcare data, it's not ground truthed. So which means that you have to use, the best case scenario in a lot of cases. And for the absolute length that what John is talking about will be very dependent or very sensitive to the actual data that we can find for our processing purposes. And in order for us to find out if it's the most optimum or not, we actually have to have a human looking at our results and grade that. And as you know, that's not an easy thing to do. So that's what I'm saying. My answer is going to be very unimpressive to a very impressive question. So yeah, so I think the short answer is going to be mostly trial and error, mostly domain sensitive, and depends on us testing a subset of the queries and by humans. We need subject matter experts. I mean, none of the system that I talked about today can be implemented without subject matter experts. They are vital for these kind of systems. Our AI is not at that level yet.
Yeah. And another question from John: how does this method of unstructured text processing handle the existence of concrete dates and/or times present in the unstructured text to determine if the concept is relevant to the current medical condition?
That's a very interesting question too. And this is actually something that we have done. You would be surprised to know, or maybe you would not be surprised to know, that there are about 40 to 42 different ways of writing time in English. This is like,
follow the ISO.
Yeah, that tells you that I have looked at this, right? I have the numbers. Yes, like 17th of March, 24th of March, March 24. There are really 40 plus ways of writing things, and we do actually have ways of. This is purely NLP problem, which actually we can identify those dates of all these different variations, and we can actually collapse them into kind of one. We call it kind of like a frame. It's a semantic frame, which has a number, which has a month, which has a date. So first you identify a piece of text as time or date, and then you say whether it's a time or a date, and then you find out what different formats it matches into, and then you convert it into a common frame. So yeah, it can be done. It is not 100% accurate, but it's not that bad. NLP is
specify it for a particular region, because I mean, common notation here in the US versus in another.
Yeah, exactly. Like the British system would put the date before and then month, right?
Yeah. I know. I always mix that up with all of my fellow SNOMED colleagues, and we get many things where we're fighting on document.
So we also have to understand where the document is coming from, right?
Yeah.
I mean, and to be honest, I remember, and I'm not talking about this particular work that we have done, but I remember working with a consultant from England, and they looked at some of the patient data that I was working on, and this was like a few years ago. And instead of looking at what our software did, he started complaining about how none of this actually is English. These were notes written by American doctors, of course, right? And to a doctor trained in England, they didn't look like proper English, right? And he said, "Well, this is confusing. How does your machine do any, understand any of this stuff?" So yes, so domain naturalization or customization is a big factor. You have to understand where the document is coming from, because the models.
Oh, sorry. Another question in the chat box came in. Can we use other forms of data, such as visual data, to extract diagnoses along with text data?
I hope one day we will. As you probably know, that there's a lot of work being done, and I have done some of it, but not a lot, of automatically looking at images or scenes and then creating captions. So, for example, if there is a boat on a river, they will say a boat on a river. So you have to identify the river and they identify the boat, right? And then you write a caption that says boat in a river. That's a much harder and it's a much early phases of what we can do. In order for us to actually identify, for example, say CT scan and describe that what we are seeing is not easy. So I would say that we are not there yet. Yeah, we have started identifying areas, image processing, and we have started using kind of very simple grammar to start writing sentences by machines. But it's not at the level of writing what the pathologists are writing.
Let me just do a time check. Oh, we're good. So a question from Mark. Following on from the time frame question, are you looking at using context associated with those dates to try to identify whether conditions are current, chronic, in remission, or whether treatment has been completed ongoing? Obviously, those things can change frequently over time when patients have recurrent diseases and symptoms.
Exactly right. And this is a very good question as well. Yes, so every data that we identify with a SNOMED tag comes with a date tag. So it's a tuple, it's a two tuple always, and exactly precisely because of the reason that Mark pointed out. I will give you a very simple example. I have seen data where a patient contracted or suspected of getting COVID, got tested negative, and then it was negative, and a few days later tested positive, and then went into treatment. Few days later tested negative again, right? So if and we are getting, as we are processing the text, we are getting positive, negative, positive, negative, right? If we do not understand what the context of the time is, then understanding this is actually absolutely impossible. So for processing chronological data, there are actually different types of algorithms, and the stuff that I showed you used transformer models, and the transformer models are really good in these cases because it can actually track chronological data. So it can actually take a transactional data into chronological data basically, and then model that. So yes, the date component is extremely important because it gives us context within it, and then we can use that to look at progression, for example, of a disease. We can look at how the disease went up and down. For example, for a disease that has a viral component test, we can actually take a look at the viral load and see how that goes up and down with time, and the treatment, and then correlate them and say, okay, for this particular patient with this particular background, healthcare background, this particular treatment, caused this kind of pattern, and if we have enough data, then we can start generalizing and say, what, for this kind of patients with this kind of background, that particular treatment would probably be better than other type of treatment. So there's a lot of things we can do, and which we can't even do right now.
Let me check the time. So we are at time, but if you have a couple more minutes, we can just answer these last two questions, Fuad.
Absolutely, yeah. Please.
Okay, thank you. Next question from Teresa. Oh, it's late for you, Teresa. Kudos to you. Is your expected customer for the secondary use of data rather than primary use? Interesting.
So if I understand the question correctly, Teresa is probably asking whether this software would be used more for, after the fact processing.
That's what it sounds like, what she's asking. Yes.
Right. Okay.
Yeah.
So the answer is, I think it can be used for both. But right now, the way I think I presented this in the findings in this particular webinar, most of it is after the fact, because these are written down, right? So I would say the lower hanging fruit, if I can use that, that phrase, I would say that after the fact is where probably the earlier applications are going to be. And then later down the road, probably we're going to go into more real-time applications.
Especially with some of what you presented, where it can be shown, and as you said, to answer the first question, it can be used as a layer on top of. Yeah, sounds like a lot more for, but I mean, eventually, possibly, fingers crossed.
Yeah, and it's also,
point of
right, NLP is also, and NLP and machine learning are also slower. There's a lot of computational aspects involved, so a lot of it is not real time, right, yet. Or in order to make it real time, you have to be really, to be using very expensive hardware. So not always available, right?
No. Okay, and we'll go ahead and wrap it up with this final question for tonight. Or today, depending on where you are, how is negation calculated to make a determination between a negative assertion versus a positive assertion for identifying the presence or absence of a medical condition?
Yeah, that's a very interesting question as well. So we actually have a module that looks at how you can say negative things. So for example, somebody does not have these things, and then again, I'm gonna go for this COVID example, and we have found there are 8 or 9 ways of saying somebody is COVID positive. Different doctors have their ways of saying things. So these are, a lot of them are, what we basically do is we identify negation first, and then we identify the association with the negation. What is it associated with? What concept is associated with? And then the success for our case would be if we can tie them successfully together. Unfortunately, in sentences, sometimes we don't do a very good job. And sometimes we can actually end up in a situation where negations are missed. In that case, we actually get a very bad result, of course. But one of the things I really just want to point out is that a lot of the stuff that I talked about may not be terribly accurate on an individual basis, but as we go and scale up into a population level, the fault tolerance becomes really good. And even at 60–70% accuracy of individual concept tracking, we get excellent results because of the sheer number of data. And this is one of these promises of machine learning, because as you see millions and millions of data points, we usually get better, which is very interesting from a computational perspective.
Well, at that, thank you so much. This really truly was a master class in informatics tonight. This was excellent. Thank you so much, Fuad. And thank you to all of you who were able to join us live. This recording will be up on our YouTube channel in just a couple of days. And hopefully you're able to catch it there as well. If you have any questions, follow-up questions for Fuad or for myself about SNOMED CT, my email is on the slide, sro@snomed.org. You may email me and I will get your follow-up questions to Dr. Rahman. Other than that, thank you all. I will see you all at the next webinar. Thank you again, Fuad, and thank you, everyone. See you next time.
Thank you.
Thank you.
Bye, everyone.